So far, we've talked about how stars are formed and how they live out their life cycles on the main sequence and then evolve off of the main sequence. And today we're going to talk about the really cool stuff, like what happens when a star dies. So we're going to talk about very exotic forms of matter like white dwarfs, neutron stars, and we'll touch on black holes at the end and then have a whole lecture about black holes next time. And so if stars are born in a stellar nursery, then what happens when they die is they'll be left in a stellar graveyard. So to review, all of your stars are going to start in a gas cloud in interstellar space, and depending on the mass, it will either evolve into a low mass star, which would be like our sun, evolve into a red giant when it stops using hydrogen into helium in its core, and then when it dies, it'll blow out its material in a planetary nebula, and what will be left is a white dwarf, which is the exposed core of that low mass star. For a high mass star, still start from your gas cloud, and when you move off of the main sequence, you'll become a supergiant, and then at the end of your life, you'll blow up in a supernova, recycle your material back into the interstellar medium, and depending on how much mass you have, you'll end up either as a neutron star or as a black hole. So today we're going to focus on neutron stars and white dwarfs. So does anyone remember what the mass cutoff between a star forming a white dwarf or exploding in a supernova? So it's 8 solar masses is what determines whether you are a high mass star and you'll become a neutron star or a black hole when you die, or a low mass star where you'll just leave a white dwarf. The 0.08 is the lower limit for what makes a star, and then 200 solar masses was the upper range of what can become a star. And 80 was just something that had an 8 in it, so to trick you from the 8 solar masses. Okay, so before we start talking exclusively about white dwarfs and neutron stars, we need to talk about what happens when stars in binary systems evolve. Because remember we said that half of all stars are in binary or more, so you can have 3 stars in a system or 4 stars in a system. So what happens to stars that evolve with a partner, basically? So depending on the initial masses of the stars, they're not going to evolve at the same rate. So this is the algal system, and you have 2 stars that are different masses. The one on the left is a higher mass star, and so it will evolve more quickly and reach its supergiant phase. But now as a supergiant, it's actually less dense than its neighbor. And so if you're close enough together, the companion star can actually steal some of the material from the outer layers of the supergiant. And so now, if you steal enough mass, now you're not a low mass red star, now you've become a high mass blue star by stealing some of the mass from your companion. And so this process of stealing matter is going to be important when we talk about what happens to things like white dwarfs or neutron stars in binary systems. And so what started as a low mass star and a high mass star evolved quickly. Then the low mass star started stealing some of its mass, and you ended up with a system that had two high mass stars, basically. So keep that in mind when we'll talk about white dwarfs, and then we'll see what happens to a white dwarf in a binary system. So we've talked about white dwarfs before. These are the exposed cores of a dead low mass star, and they're basically a big ball of carbon, but that carbon is under immense gravitational pressure or gravitational energy trying to make it compact, and the only thing that's stopping it from collapsing is electron degeneracy pressure. So that's the quantum mechanical effect that electrons don't like to be in the same quantum states, and so that provides a pressure that counteracts the inward force of gravity. And so the Sirius system is a multi-star system, and it has a white dwarf in it. And depending on what wavelengths you look at the system, you'll see different objects being brighter than the others. So Sirius A is the normal star, and Sirius B is the white dwarf. So if you look at the system in visible wavelength light, you'll only see Sirius A, but if you look in ultraviolet and X-ray light, you'll see Sirius B actually looking brighter because it's the hot core of a dead star that's being exposed. So to review, you've got your main sequence doing hydrogen into helium in your core. Then once you have done the fusion reactions enough, you'll have this helium displacing all of the hydrogen in your core, and it's not yet hot enough to do a fusion reaction with helium, so you get this hydrogen burning shell. Then eventually the helium core will heat up enough to do fusion. The fusion of helium will result in carbon. Then you build up enough carbon in your core, and you get it'll displace the helium, so now you have a helium fusion layer and a hydrogen fusion shell, and that double shell fusion is unstable, so eventually the star blows itself apart and it leaves behind a planetary nebula and that carbon core, and that carbon core is what becomes the white dwarf. And so once you have your white dwarf, there's no more energy coming from inside of it, there's no nuclear reactions, and so it'll just slowly radiate all of its heat and energy out into the universe and become dimmer and cooler as it ages. The sizes of white dwarfs, so it's dependent on its mass. If you have a mass of about 1 solar mass, then that white dwarf will be about the size of the Earth. But if you increase the mass on your white dwarf, you actually make it smaller. So this is similar to what we saw with the gas giants. If you keep adding mass to your gas giant, it does get bigger up to a point, but then if you keep adding mass, you'll actually start shrinking the radius a little bit because there's the outer layers are adding extra mass and compacting the inner layers. But there is a limit to how massive you can make your white dwarf. So there's this thing called the Heisenberg uncertainty principle, which is this equation on the right. the triangles here mean uncertainties. And what this equation is saying is that the more certain you are about an object's position x, the less uncertain you are about its momentum p, or vice versa. The stuff on the right are just constants, and they're very, very small. So when you keep adding mass to your white dwarf, you're making it more and more compact, so you're leaving less and less space for your electrons to exist. So you're decreasing the uncertainty in the position, and therefore you're increasing the uncertainty in your momentum. If you do that enough, you get to where your momentum means that your electrons have to be moving at the speed of light. And we know that nothing should be moving faster than the speed of light. The mass limit that causes that speed of light velocity is 1.4 solar masses. So if you have a mechanism to put extra mass onto your white dwarf, and you put enough onto it that you exceed 1.4 solar masses, you have a bad time. And we'll talk about what happens to white dwarfs over 1.4 solar masses in a second. So naturally, if you just have a white dwarf by itself, it will never exceed this 1.4 solar mass limit, and that limit is called the Chandrasekhar limit, named after the person who did the complicated math to figure out what this exact mass number would be. So we know that stars evolve in binary systems. So what happens if one of the stars goes through its life cycle faster and it becomes a white dwarf, but it still has a companion star? So just like when you had two stars next to each other, the white dwarf could steal some material from the companion star. So we've got material moving from the star towards the white dwarf. Due to angular momentum, it will start orbiting the neutron or the white dwarf in an accretion disk. And just like you have when you had solar system forming disks, you would get lots of friction and things heating up. Any accretion disk around a compact object is going to heat up and start emitting its own radiation. And so you can detect these accretion disks, especially for bigger things like black holes that we'll talk about next time. So this is one way to observe an object that's very small that you might not be able to see directly, but you can see the accretion disk around it. Eventually, some of that material is going to fall onto the white dwarf and not just orbit around it in this accretion disk, and you get explosive results, basically. So the material that you're going to be pulling off of this star is going to be hydrogen. Stars are mostly made out of hydrogen, and the outer layer is what you're pulling material from, and that'll be the least dense material that the star is made out of, so that'll be hydrogen. The white dwarf is the core of a dead star, so that could be a very hot object if it hasn't had a lot of time to radiate its heat out into space. So if I take some hydrogen and I put it on a very hot surface, then that temperature could be enough for that hydrogen to start doing nuclear reactions. So when that happens, we get what's called a nova. So this is an explosion that happens when this material around the white dwarf becomes hot enough to start doing fusion reactions. And so the star system will temporarily become brighter, and so they're very easy to spot out in space. You just look for something that becomes brighter all of a sudden, and it will blow any of its accretion disk material out into space. So this is a Hubble image of a nova system. So you can see the very bright nova in the center, and then this is all the material that's been ejected out into space. So what happens if a white dwarf accretes enough matter to exceed the 1.4 solar mass limit? Yeah, so it's going to explode. You're going to need a lot more mass and a lot more density to make something become a neutron star. So it turns out there are two types of supernova explosions. The one that we've seen so far, you just have a massive star reaching the end of its life cycle, and it reaches a limit, and it turns out it's the same mass limit due to the same Heisenberg uncertainty principle, and it will collapse into either a neutron star or a black hole, and there will be this big supernova explosion. But it turns out there's another type of supernova that can happen, and it's because a white dwarf has exceeded the Chandrasekhar limit. And so they're both supernova because when they were discovered, they were just very bright flashes of light, and then it took many years to figure out what exactly was the mechanism that caused those explosions. But you can tell the differences between them in a couple of different ways. So one way, if you track the light curve, meaning if you plot the brightness of the source over time, then for the massive star supernova, they're not gonna be as bright to start, but they'll last a bit longer than the white dwarf supernova. And then the white dwarf supernova will be very bright initially, and then it will fade more quickly. But that takes a lot of time to do. So the other way that you can do it is by looking at what elements are found in the spectrum of those events. So we talked about novas and supernovas. A supernova is going to be many, many, many more times brighter than the nova, 10 million times brighter. For a nova, you're doing hydrogen into helium fusion from that layer that is around the white dwarf, but after that explosion, the white dwarf will be still there, and you can have recurrent novas. So the same white dwarf can do novas several times. But if the white dwarf is in a supernova, then it completely blows itself apart, and there's not going to be anything left behind. And for the different types of supernovas, so we saw their light curves are different, but the big difference is that their spectra are different. So a white dwarf that blows itself up is made out of carbon, so it's not going to have a lot of hydrogen absorption lines at all. Whereas the massive star that went supernova was made almost completely of hydrogen, so there's going to be a lot of hydrogen to have these absorption lines. The really interesting thing for the white dwarf supernovae are that we will use them for standard candles in cosmology. So when we talk about how the universe has evolved, in the 1990s, we discovered that not only was the universe expanding, but it was expanding at an accelerated rate. were able to make that discovery using these white dwarf supernovae. So we'll talk about that in a couple weeks. So the white dwarf is the leftover core of a dead star. It's made out of electron degenerate carbon, and that electron degeneracy is what balances out the inward pull of gravity. Many stars evolve in binary systems, and so you can have a white dwarf as one of the members of those binaries. And if it steals a little bit of matter from its companion, you could have a nova. But if it steals too much matter, then it will blow itself up in a supernova. Okay. Then the next thing we'll talk about are neutron stars. So what is a neutron star? How did we discover it? And just like with white dwarfs, interesting things can happen to a neutron star in a binary system. So the neutron star is the leftover core of a massive star that has gone supernova. And it will also have a degeneracy pressure that's holding it up against the inward pull of gravity, but it's going to be neutron degeneracy pressure instead of electron degeneracy pressure. At the very end of a massive star's life, the pressure on the core, this was an iron core, is going to be so great that your protons and electrons will start to fuse together to make neutrons and neutrinos. So this is why what's left at the core of the massive star is just neutrons. So you have a ball of neutrons that's left over, and so that's why this is a neutron star. So has enough matter or mass that it could be a star, but all of the matter that makes up the star is all neutrons. So we had the size comparison for a white dwarf. For a neutron star, it's even more compact. So this is a map of our area, and so the neutron star is about the size of a city. And the radius of a neutron star is about the size of a small city. So you're compacting as much as, let's say, one solar mass in the size of a city. So it's a very, very dense object. So how can we discover these things? They're a ball of neutrons, so they're not going to be doing fusion reactions, and they're very small, but there's a lot of energy associated with them. So in the 60s, Jocelyn Bell was looking at radio data, and she saw that there was a radio source that would pulse at very regular intervals. And it was always this very precise timing between the pulses. So the way that you can get something pulsing in space is to have something rotating. So we'll see the math that you do in a moment to calculate what this must be, but it turns out that these are the pulses of a rotating neutron star. And so if the neutron star is pulsing, then we call it a pulsar. The Crab Nebula has a pulsar. So remember, this was the supernova remnant that Chinese astronomers saw in the 1054 AD time. So they saw the bright light from the supernova, and now like 1,000 years later now, we know that we can see the supernova remnant, and we can see the pulsar at the center of the supernova remnant. This is the Crab pulsar, and so this is what it looks like. It has a period of 0.03 seconds. So every 0.03 seconds, this thing is flashing, which means it has to be spinning very, very quickly. So this pulsar is spinning 30 times per second. But this is something that has the mass of the sun that's spinning 30 times a second. So what exactly is a pulsar? A neutron star has a very strong magnetic field, and it will beam radiation due to this rotating magnetic field. And depending on your line of sight with this beam of radiation, you can see the flashes of the pulsar. So you can imagine this being like a lighthouse that has a rotating light that's flashing out at sea. So if you do some basic math, we can calculate the radius of a neutron star. If we time the pulses that we see, we can get a rotation rate. And using the radius and the rotation rate, we can calculate the speed that an object on the surface of the neutron star must be traveling. And so when you do that calculation, you see that the material on the neutron star has to be moving at a considerable fraction of the speed of light. And there's basically not any other form of matter that you can come up with that would be stable enough to rotate this quickly and not just rip itself apart with each rotation. So due to how fast these things are rotating, we know that they have to be made out of this very compact ball of neutrons. So if we had, let's say we are talking to another civilization out in space, would we necessarily agree that a given neutron star is a pulsar? So this one is true. So the only way you see it as a pulsar is if you're directly along the line of its radiation. So there's different orientations that you could be in where the neutron star is spinning, but the beam of radiation never points at you. Okay, so neutron stars can be in binary systems. So what happens to those neutron stars? Just like the white dwarfs, they can steal material from a companion star, and it will form an accretion disk around the neutron star. So we said that the rotation rate of a neutron star is very stable, and we actually use these for some very interesting physics that maybe we'll talk about at the end of the semester using pulsar timing arrays. But if you get material rotating around the neutron star in the same direction, then you can actually increase the spin rate of your neutron star. And that material can eventually fall onto the neutron star, and the neutron star is going to be very hot because it was the core of a star, and any material that's going to fall onto the neutron star is going to be hot enough to fuse. So for example, if helium falls onto the neutron star, it will be hot enough to fuse, and it will emit these X-rays. And so another phenomena that you can look for out in space are X-ray bursts. And so these are kind of an indirect way of detecting neutron stars. And they are very shortly lived, so this is only a second or two, but it's emitting more X-rays than you're going to be getting from, say, a normal star in a very short amount of time. But it's not just a neutron star that is orbiting another star. What if you had two neutron stars orbiting each other? What happens then? So that's what this video will be about. Now it's probably too loud. So these are two neutron stars orbiting each other. And in 2017, we, as astronomers, observed the first merger of two neutron stars and the associated electromagnetic radiation that comes off of those. So these merging neutron stars can generate gamma ray bursts, and so that's going to be the material ejected along the poles of the merging system. But if you're not aligned with these poles, then you're not going to see the gamma ray burst. So it turns out, for this pair of neutron stars, we first detected it using gravitational waves. So as two massive objects spiral in towards each other, they will emit gravitational waves. We've seen the detectors that we use to detect those gravitational waves. And then we weren't exactly along the line of the gamma ray burst. We were a little bit off to the side, but due to some relativistic effects, as this gamma ray burst spreads out into space, its opening angle eventually was aligned so that the Earth could see it. So this is the first and so far only time that we've detected the gravitational waves from a neutron star merger and the electromagnetic waves from the same event. So that was a very important discovery. And so what you can do is you can turn that gravitational wave frequency into a sound, and so this is what a gravitational wave merger might look like. And so this is probably this might be for merging black holes, but this could also work for merging neutron stars. And so as they spin closer together, you're getting an increased frequency for your gravitational waves, and then eventually they're going to merge and everything's going to go haywire. And eventually it'll settle down into a new stable signal. So just by studying the frequency of the gravitational waves, you can do a lot of complicated math to figure out what the two masses have to be to create those gravitational waves. And depending on what those masses are, you can determine what the two objects that were spiraling in towards each other had to have been. And so what if the material that falls onto the neutron star happened to be orbiting in the opposite direction as the neutron stars spin? So if it's going in the opposite direction as the spin, then it'll slow down the rotation of the neutron star. So this was the same principle that worked when we were talking about navigating through the solar system, and we talked about gravity boosts. So you can go in the same direction as a planet to speed yourself up and steal some of its energy. Or if you go in the opposite direction as the planet spin, then you could slow yourself down. Say, for example, if you were at the planet you wanted to orbit. So it's all the same principle, and that's conservation of angular momentum. So just like there was a limit for the mass of a white dwarf, there's also a limit for the mass of a neutron star. And that's about 3 solar masses. So white dwarf limit was 1.4 solar masses, and neutron star is about 3 solar masses. So then I'll let you guys talk amongst yourselves for a minute or two. What happens if you exceed the neutron star mass limit? What happens when you exceed the neutron star mass limit is you get a black hole. So these are artist representations of what a black hole might look like, and next class we'll talk about black holes in more detail. So this is kind of a useful picture. So for a low mass star, you'll have enough gravity basically to compress all of your carbon atoms into a small enough state that your electrons don't really have any room to move, and so they'll all be in the lowest energy state. But that electron degeneracy pressure will stop the white dwarf from continuing to collapse. For a neutron star, you have enough mass to overcome this electron degeneracy pressure, and there's enough mass to start the protons and electrons fusing together to make neutrons. So now I've got just a ball of neutrons in the core of my star, and there's a neutron degeneracy pressure that supports the weight of all of these neutrons from collapsing any further. But that mass limit is about 3 solar masses, and if you exceed that, then potentially there's nothing left to support your weight against gravity, and you just collapse into a black hole. There might be an intermediate type of object that we have not yet detected, but that has been theorized, that's called a quark star. So protons and neutrons are not the basic building blocks of matter. There are these things called quarks. So electrons are basic. There's nothing that you can break an electron down into. But using things like particle accelerators, we can break protons and neutrons into these subatomic particles called quarks. So people have theorized if we can get neutron stars, then maybe we can get quark stars that are held up by some quark degeneracy pressure, and that will have some slightly greater mass limit than a neutron star. But eventually, there's no known forces that can support your weight against gravity, and over a certain mass limit, you're going to be collapsing into a black hole. So these neutron stars are basically the core of a massive star that has exploded in a supernova, and the core is just a ball of neutrons that are supporting themselves by this quantum mechanical neutron degeneracy pressure. We first discovered them by observing these very fast rotating objects in space, and those rotations made them pulse. And the only object that would be able to rotate that quickly and not blow itself apart was basically a neutron star. And you can get neutron stars in binary systems where they can steal some of the matter and create these these flashes of X-rays. So those are called X-ray binaries. And the sudden fusion that happens when they pull that material off is called an X-ray burst. And if you have two neutron stars that are orbiting each other, they can spiral in towards each other, emit gravitational waves, and when they merge, they will blow themselves up in what we call gamma ray bursts, or GRBs. So next time we'll talk about black holes and how we observe them and all the wacky physics that happens when you're dealing with black holes.